This video is on simplifying radical expressions. In a previous video, I've explained how to simplify radicals and then how to simplify radical expressions separately. So radicals with numbers and then radical expressions with just letters. This video is going to be simplifying the radical expressions with numbers and variables. So you don't want to try and do these problems as one huge problem. You actually want to separate them as the two individual types, the ones with just numbers and the ones with just letters. So in this case, we have the square root of 20x y to the fourth z to the third. So again, instead of just seeing it as one big problem, if you separate them into the square root of the number and then the square root of the letters, it will make things much easier. So this is the same thing as saying the square root of 20 times the square root of x y to the fourth z to the third. Now we just go about simplifying them the same way we have been. So we'll simplify the numbers by finding the biggest perfect number, so biggest perfect square in this case, that goes into our number, into our radicand, and then we'll look at the letters. Now again, there are multiple ways to simplify the radical expressions with the letters. I'm going to use this method where I take my index and I divide my exponent by my index. So the first part is the square root of 20. So I want to take the square root of 20. I want to know the biggest perfect square that goes into 20, which is 4. So this is the square root of 4 times the square root of 5. So I know that the square root of 20 will become 2 square root of 5. I don't do anything with that yet. I know I will have to do something with it later. And now I look at the letters. So I can write out the x's, the y's, and the z's. Now I look at my index, which in this case is nothing written there, so I know it has to be a 2 because it's the square root. And I can determine if I can simplify or not. The index needs to be smaller than the exponent to be able to simplify. So the 2 is not smaller than the 1, so the x's will not simplify. So I actually know that this will have to stay as the square root of x to the first. I cannot simplify the x's because it's not, the exponent is not big enough. For the y's, we do have 2 is smaller than 4, so I know that the y's can simplify. That means I can take my index of 2 and determine how many times does it go into the exponent of 4. It will go into 4 2 times with a remainder of 0 because it goes in there perfectly. What that tells us is that this 2 is the exponent of our coefficient of y. So I can have y to the second as a coefficient, and I have no exponent in my radicand, so I don't have to put a radical on my y's. For the z's, I look to see, can we simplify it? 2 is smaller than 3. That means I can simplify it. So I look to determine how many times does 2, the index of 2, go into the exponent of 3. 2 goes into 3 one time, but it does have a remainder of 1. So again, what this does, how many times it goes in there perfectly, this becomes the exponent of our coefficient of z. So I know I can have z to the first as a coefficient, but then I do have an exponent for my radicand. So that means I have to have a radical, and it has to still be the square root, because we originally started with the square root. I have an exponent on my radicand, which again is my z to the first power. Now that we have actually simplified each individual part, we've simplified the number, the x's, the y's, and the z's, we can put them all together. So as previously stated, we put all of our coefficients together. All of our coefficients will multiply to each other. So if we look at our number first, because that's the first thing we did, our coefficient is 2. So this is 2. Our coefficient for the x, there is no coefficient for the x, so I don't put anything with my 2 yet. go to the y's. The coefficient for the y's is y squared because this is not in a radical. I know this is a coefficient, so I put my y squared attached to my coefficient of 2. Then I go to the z's. The coefficient of the z's is z to the first because this is on the outside of the radical. So I can put z to the first with my other coefficients. I've gone through each of the 4 different things, so I had one number, 3 different letters. So I've done 4 different things. Now I have to go to see if I have any radicands, if I have a radical left over. If I look at my number, I see that I automatically have a radical, so I can go ahead and put a radical symbol. And remember, this is a square root, so you can put a little 2 in there. You don't have to, but it is a square root. So now I need all my radicands. So I go to my number first. My radicand for my number is 5. Then I go to the x's. The radicand for the x's is x to the first because this is inside the radical. The radicand for my y's, there is none. There is no radicand for the y because there's no radical on the y's any longer. For the z's, my radicand is z to the first because this z to the first is inside the radical. So I can put z to the first inside the radical. And this is our final answer. We have simplified it completely by doing the individual parts instead of one huge problem. If you do the individual parts, it makes things a little bit easier. If I go on to this next problem, number 2, it is the square root of 16r to the 7th. So this time we only have 2 things. We have one number and one letter. So I want to look at the square root of 16 times the square root of r to the 7th. Because those are the 2 different things I'm looking at. So for the square root of 16, this is actually just 4. So I can write down 4. It's not the square root of 4, it is 4. The square root of 16 is just 4. For r, I do need to write out, for my r's, the index is a 2 in here. So I need to know how many times does 2 go into 7. Now I know that I can't do this because 2 is smaller than 7. 2 goes into 7 3 times with a remainder of 1. That tells us that our exponent on our coefficient of r will be 3. So we'll have r to the 3rd power. And then we have a exponent left over, so that means we will have a radical. This is still the square root. We have the exponent of 1 on our radicand of r. So now to put all these together, first we look for our coefficients, all of our coefficients, numbers. The coefficient is 4. Letters, the coefficient is r cubed. Now we look for radicals. For the number, there is no radicand left over, so I don't have a radical yet. For our letters, we do have one radicand, so that means I will have a radical, and I will have a radicand of r to the 1st. And this is our final answer. You do not have to put the 1 on the exponent, but it is good to always know that that came from your remainder or from the how many times it went in perfectly. On problem 3, this goes back to a square root. This is 4 square root of 12, a squared, b squared, c to the 4th. So again, we're going to separate these as 2 values. So we have 4 square root of 12 times the square root of a squared, b squared, and c to the 4th. For the numbers, we actually have a coefficient already. And again, just like before, the coefficient will just multiply to the coefficient we're able to simplify. So we'll keep this 4 on the outside times the square root of 12 is really the square root of 4 times the square root of 3. So what we have here is 4 from the original coefficient times the square root of 4 is 2 times the square root of 3. So our number, we're just going to write our number out, becomes 8 square root of 3. That's just our number. Now we're going to do our letters. So again, our letters have an index of 2. So for our A, B, and C, 2 is smaller than or equal to 2, so that's good. If it's equal to, it's going to be a perfect match. That means that the square root of A squared is just going to be A. So we can make sure that that works. The 2 is smaller than or equal to 2. So for A, we can simplify that. 2 is smaller than or equal to 2, therefore B's will simplify. And for C's, 2 is smaller than 4, so the C's will simplify. So again, we do 2, the index goes into the exponent for our A's. The index goes into our exponent for the B's. And our index goes into the exponent of our C's. For A's, 2 goes into 2 one time perfectly, so there is no remainder. And that makes sense because the square root of anything squared is just the thing that it is, the radicand. 2 goes in, for the B's, 2 goes into 2 one time with no remainder. For C's, 2 goes into 4 two times with no remainder. So again, I'm just going to write out what this really means. For the A's, we do have a coefficient of a to the first, but we have no radicand. And again, this makes sense because the square root of a squared should just be a, and that's what this is. The square root of b squared should just be b, so we have a coefficient exponent of 1, so b to the first with no exponent in our radicand. So the square root of b squared is b. Then we had, for the c's, we had an exponent for our coefficient of 2. So we have c to the second power, but again, no exponent in our radicand. So to put everything together, again, let's go to all of our coefficients. So go to your number first. The coefficient of our number is 8. The coefficient for our a is a to the first, so I'm just going to put a. The coefficient for the b's is b to the first, which is just b. The coefficient for c's is c squared, so I will need to put c squared. Now to look for our radicands. On our number, we do have a radicand left over, so I do need to put the square root of 3. For the a's, there is no radicand. B's, there is no radicand. C's, there is no radicand. So our answer actually just stops there. So it becomes 8ab squared, square root of 3. And this is our final answer. On this last example, we have a cube root. We have a cube root of 686, j to the 25th, and t to the 92nd. So these are much bigger numbers, but we're still going to do the exact same process of what we just did. So we do have a cube root. I'm going to separate these into numbers and letters. So we have the cube root of 686 times the cube root of j to the 25th and t to the 92nd. So looking at our numbers first, we want a cube root. The cube root of 686, so we look for the biggest perfect cube that goes into 686. This would be the cube root of 343 times the cube root of 2. So our numbers, again, we have to make sure we keep our index. We cannot drop off our index. The cube root of 343 is 7. And then we're left with the cube root of 2. So we have simplified our number. Make sure you're careful about writing that index Otherwise, it becomes a square root, and we're not allowed to do that. Next part is our letters. 3 is smaller than 25, and 3 is smaller than 92. That means we will be able to simplify both letters. So J's will simplify, and T's will simplify. So for the J's, I want to know how many times will 3 go into 25, and for the T's, how many times will 3 go into 92. So again, we want to know how many times will it go in there perfectly. 3 will go into 25 8 times perfectly, because 8 times 3 is 24. Then we're going to have a remainder of 1. For the T's, 3 goes into 92 30 times, because 3 goes into 9 3 times. 3 goes 30 times 3 is 90. So that means we have a remainder of 2. So again, what does this mean? We have an exponent on our coefficient, exponent on our radicand. Exponent on our coefficient, exponent on our radicand. That means we will have radicals left over. So we have j to the 8th, and then we'll have the cube root, we have to keep our index, of j to the 1st. Or we can just put j. For the t, we'll have t to the 30th, and then the cube root of t to the 2nd power. Now to just put it all together. All of our coefficients start with your number first. The coefficient of our number is 7. The coefficient for the j's is j to the 8th. Coefficient for the t is t to the 30th. Then we look to see if we have radicals. So for our number, we still have the cube root of 2, so we will have a cube root no matter what. So our radicand so far is a 2. Then for our j's, we have a j to the 1st, which we can just put as j. And then for our t's, we have t to the 2nd. So it's t to the 2nd inside of our radical. Now we can also check 3 is bigger than the 1 on our j, and 3 is bigger than the 2 on our t. So that lets us know that we cannot simplify the letters any further. And the cube root of 2 would just give us a decimal. So this would be our final answer.